Okay, let's start. In the last week, we have finished with failure mode and effects analysis, and that's a very important method in order to find out what failure causes and what failure results are. And it is a very systematic method, which initially was only aimed at finding out, let's say, for one failure, the cause and the effect, and only later on system FMEA was designed. In that way, a complete system must be structured, and a system means it can be some product, or it can be a process, or it can be a combination of both. So in that way, you can find out what an effect, let's say, on the layer or on the level of some process, for instance, having an effect on an adhesion, or having an effect on some particle contamination, what that if that can cause failure on a system level, which in the end is a safety effect. Okay, so in the first step of that method, we must structure the system. So structuring is top-down method. On the other hand, the failure propagation goes from lower level to higher level, so it's a so-called inductive method. But I would say, maybe a little contrary to normal textbooks, FMEA is both a top-down and a bottom-up method insofar as the system is structured. We have a system, subsystem, sub-subsystem, and so on, like a car, a powertrain, gearbox, gearbox controller, microcontroller, and so on. And in that way, we structure the system. To all of the system elements, we assign functions. So how does that sub-element contribute to the function of the element or of the higher level system, and so on. On the other hand, if it doesn't function, it's a failure or a fault. So also we can say for one individual function, like driving, there can be, of course, many different failures, like car stops or car sliding or something like that. And so we can have a failure propagation. Now that's the inductive method. And then each failure is assessed with that risk priority number. RPN is occurrence probability of the failure, the severity of the failure result, and then we have also the detection probability, which gives us information if the cause of such a failure could be detected, and in that way we cannot avoid the failure really, but we can or we cannot generally avoid the failure. It still can happen in principle, but of course by detection we can reduce the probability that the failure will have an effect. Okay, in the end we must go to the system optimization, and here we have seen we need such a chart, and in that chart we do not just put in the data on severity occurrence probability and detection probability, but we also have recommended actions. We have responsibilities. And after the action, again, we make a judgment of severity, occurrence probability, and detection probability. And so, of course, we want to reduce the risk priority number, and we must say such a sheet is assigned to each individual system element. So we need lots of such sheets, and of course, such sheets are they are connected to each other. Okay, now let's have a look at the individual judgment of these risks. And so we have severity. That's here for the example of automotive industry. If there is no effect on a car or very, very low impair of functionality, which can only be detected by service staff, then it has an effect of 1. And so that goes up to an effect of 9 or 10 when a car has a safety risk. So you could lose a wheel or no more braking possible or such a thing. What is also important is non-compliance with regulations. So when the Volkswagen did their diesel fraud, normally that would be an extremely high severity factor here in our FMEA, because the car is no longer compliant with regulation, and that means the car in principle is no longer allowed to drive. Okay. Functions are significantly reduced. Immediate consultation of service station is mandatory. That means, for instance, your car tells you go immediately to service. Important subsystems break down. Function reduced somewhat. Maybe you cannot have the full speed anymore, but it's not really a safety phenomenon, but more the functionality. Then we have 6, 5, or 4, or if it's a minor, that's a 2 or 3. So a low functional reduction, maybe your radio doesn't work anymore, and so on. Then have a look at the occurrence probability. When in 10% or 50% of cases this failure can occur, that's a very high occurrence probability. Typically, that's the effect of some misdesign. Yes, when the design when a very severe mistake was made, a miscalculation, for instance, a part is not strong enough or such a thing, or a systematic error in a software which appears, let's say, in any car of a series, then it's a high occurrence probability. On the other hand, if it's only 1 in a million, then we have a 1, which is very good. And in the end, to judge something below 1 ppm is hardly possible, because here there are many effects of chance, so it's quite arbitrary if something happens here or not. So that's the range in between. Let's say here moderate is something like 1 promille to 5 promille, 8 and 7 is 1% to 5% probability. On the other hand, you always must keep in mind that in automotive industry, we are always talking about series scale of 1 million cars or so. And in the end, that means 50,000 cars of 1 million have such a breakdown. That will be quite costly. Then we have the detection probability of the failure cause. And here we must say, here it is expected that by such detection measures, we have a very high probability of failure detection. For instance, it is expected to have 99.99% in order to get a Mark I here. On the other hand, a failure detection of 90%, that means 1 out of 10 failures or failure causes is not detected, is not sufficient. So that's a very high mark here, and that's not very good. So in that way, failures, if we want to look for failure detection, we must be very, very sure that we can see such failures. And of course, methods of non-destructive testing are such methods in order to find out if a failure can happen. For instance, when we make X-ray images, we can look if there are internal flaws in a tire or in an electronic component, and in that way, again, we must be quite sure. And I can tell you, when you want to have an automatic test system that has a failure detection probability of 99%, which is in between here, between Mark 7 and Mark 6, so not so good, then it is already quite hard to achieve this. Okay, now let's imagine we have all of these risk priority numbers, and then we take risk priority numbers for all system elements, and we just order them, so from largest to smallest, and then we get such a graph, which is a so-called Pareto graph. And then we start thinking about what will we do. Of course, it makes sense to start with the failures and faults which have the highest risk priority number. Yeah, so here 1,000, that is, you could say, that's a deadly failure. Of course, that's the one you must eliminate first, and then you go to the less, let's say, the less harder ones, and so on until you end up here. You could also say, when you look at the quality of a design, the quality of design is the better, the farther to the right in the risk priority number you stop taking actions. So let's say a design having here risk priority numbers, no, the risk priority number is here, and that's just the number. So a design which stops, let's say, at 200 is not so good. A design which stops at a risk priority number of 100 is very good, because the harder failures and also many more failures are eliminated. Also, one must say, when two failures have the same risk priority number, the ones with the highest severity must be eliminated first. Maybe you could say we have a high probability of a car breakdown, but we are sure nothing will happen to the driver or someone else. Then you could say we have maybe a high risk priority number. On the other hand, we have an event which is of low probability, but driver could die with a high probability. Then having two same risk priority numbers, the one with this higher severity must be eliminated first. Also, it is important that certain failures, especially such ones which have high severity, are not only reduced in their probability, but they are eliminated generally. So you could say high risk technologies are avoided. Yeah. So to say it a little blunt, if you have no nuclear power, then also a nuclear power station cannot blow up. Yes. So you have brought the probability that such event will happen to zero. And that's something else than just reducing the occurrence probability of a nuclear power station which still exists. Of course, in an aircraft you cannot avoid flying. So as long as you fly, the aircraft can fall down. But on the other hand, you can then reduce the probability of that happening. Okay, in that way, the rules I just told you are listed here again. And so System FMEA is a very important tool, not only to get data on how safe a system is, but also what makes it unsafe. And that's something which is very important. Okay, now we have some exercises, and from now on I would like to start doing exercises. And yes, let's start with exercise 4.2. We have an anti-brake locking system that consists of 4 elements which are combined as a quartet in a reliability block diagram. Each element is assumed to fail by chance. The MTTF for all elements is 1000 hours. Okay, that's not so high. Derive the formula for the reliability of the system. Compute the system's reliability for times of 0, 100, 300, 1,000, and 3,000 hours. Okay. Can you give me, do you have an idea how to solve this? And first of all, what I would also like to see is, of course, the reliability of an individual element, and also compare this value with the reliability of the non-redundant system with E1 plus E3 in a series. Then compare these values with the reliability of a redundant system with the series E1 plus E3 in parallel to the series E2 plus E4. Compute the failure rates, lambda 1 to lambda 3 of all different systems. Okay, let's proceed. We have such an element. And then we have the following cases. We have, so that's the case 0. Then we have this case, let's say, in a series. We have case 2. Okay. That could be a typical test in an exam. And now we have number 3, where we can say we have so that's the correct way to put it. And now we know MTTF is 1000 hours. Okay, what's the failure rate here? Can you give me feedback? How can we get the failure rate here? How much is lambda? And that is 1 million fit. That's a very high value. Now give me information. After 1,000 hours, how many have failed?
One has failed.
Sorry?
One has failed after 1,000 hours.
No. So let's make it in a systematic way. F of t is 1 minus e to the power of minus lambda t. Okay. Lambda is 1 divided by 1,000, yeah? Okay. F of t is 1 minus. So if t is just 1 divided by lambda, then we put it this, yeah? That's a systematic way. F of t is 1 minus, what is e? That is 2.7. And what is that? That is 1 minus 0.36 or so, yeah? So 1 divided by 3 is 0.33. Okay, 10% more, 0.36. So f of t is something 0.6. That's not quite correct. So is 63.2%. Okay. Anyway, you can compute that, but on the other hand, you should just know when you're at the mean time to failure, then in the case of a Weibull distribution and in the case of an exponential distribution, it is always 63% failed. Yeah. Okay. In that way, we have computed it. And of course, now what you could do, but that's up to you yourself, you can compute it for yourself. Okay, so here you could say, yeah, what is the failure probability? Here it's 63.2%. In that case here, the lambda is twice that. It's 2 divided by 1,000 hours. And in that way, you compute the f of t in that case. What will it be? It will be significantly higher, but it cannot be twice as high, yeah? Because that would mean 120%. So f of t at 1,000 hours is now you put that in here. E to the 1 divided by e is 0.63. You take its square. What is it? Yeah, let's say 0.15 or so, yeah? That means we have 85% probability in that case here. Yeah? What is the probability that this will fail here? So the failure probability is this will fail and this will fail. So both must happen. So here you could say f, that's f1, f2 of 1,000 is 0.85 times 0.85. And that here is yeah, let's say roughly 0.7 or such a thing. Okay. So you can say in that case you are worse than in that case. But on the other hand, here you have more system elements, yes? That's a more complex system, and you have maintained the reliability, or you have still the same failure probability by redundancy. And now the question is, how can we find out the redundancy of such a system here? And in that way, we could go 3 actions. First of all, we can say, yeah, let's try it that way. We say we have, and now let's see if that is the same like we put it here. So after 1,000 hours, one element F is 0.63. For 2 elements, what was it? E2, E3, E4. E1, E2, F, that both fail is 0.63 square. And that's roughly 0.4, let's say that one, yeah? Possibly you have a calculator and you can calculate it. And for the E4, E3 or E3, E4, so we, okay, we have also and now both are in a series, and in that way, of course, we can again say we add the failure rates here, for instance, and in that way, when will that fail? It will fail when that fails or when that fails. And in that, or we must say both must be reliable, so that if that is reliable and with that is reliable, so we can say R12 is 0.6, R34 is 0.6, and our system in that case is, what is it? R12 times R34, and that is 0.36, and the failure probability is here 0.64. In the end, what have we seen? If all elements are equal and if we have such redundancy, finally the failure probability is the same as if we would only have one element which has the same failure function. Okay, in that way we have solved it. Of course, the question was, you solve it for other times like 100, 300, 3,000 and 10,000 hours. Maybe the best is you do it in Excel, and in that way you can get the failure function over time for all 4 cases we have seen here. What is the general method? We will see it in more detail. That's the following. We have the space state method. Sorry. Space state method. And that means we have all 4 elements. If we have 4 elements, how many cases do we have then? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 cases. And in that case, we could say, okay, element 1 just can be up, so it's functioning. Or it can be down. Then we combine it in a systematic way. 1, 1, 1, 1, down, 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 down. Again, 1, 1, 1, 1, down, 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 down. 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay. Now the question is the state that this happens. What is the probability of being in the state E? Of course, that is R1, R2, R3, R4. What the probability that all have failed, that's F1, F2, F3, F4. We get all of these information from where? Of course, from the individual functions describing the reliability of the system. So for instance here, the probability would be R1, R2, F3, F4. But you could also say here R1, R2, 1 minus R3, 1 minus R4, and so on. In that way, we get the individual probabilities. Now the question, how do I get the system reliability? Here I must say, what is the state of the system? And the system state again can be described by 1 or 0. Of course, here that state is 0. Also, all cases where three elements are defective, we can be quite sure that these are failed. So let's say here that's a fail. That's a fail. And if E3 and E4 are failed, no, if E1 and E2 are failed, of course there can be no path. And then it's also a fail. So the reliability we get sum up all probabilities where system is up. So that means functioning. And failure function or failure probability all is down. And of course, you must always keep in mind R is 1 minus F. That means R plus F is 1. Okay, in that way you can do it. You can solve that whole thing. And my idea is you exercise it for yourself. Also, what I would like to check you is that when you look at the space state method for that case, yeah, and you compare it with the other method, yeah, where I have put it that way. I would like to have the answer from you next week, whether there is a difference or if it's the same result. Also, you must be aware that that could be an exam question if we end up with the same result when we do it in that method. So combining these, or if we take the space state method. What's the advantage of the space state method? It is something which is very versatile. That means we can have very many cases and we can have also special cases. The important thing is that we always must check if there is a path possible in the combination of failures and functioning elements. So that's the question of the path. And that gives you information system up or system down. And a very good method for deciding whether the system is up or down is either the reliability block diagram or the fault tree. So in that way we have combined mathematical methods with graphical methods like fault tree and reliability block diagram. Okay.